So far, we have studied the value of CV. But you know, the specific heat values can be very different depending on how the system behaves, whether it's constant pressure, constant volume, or whatever. Another important case is an isobaric process when the pressure is a constant. When the pressure is a constant, we can also calculate the value of specific heat per mole when the pressure is constant. So dQp, here P means the pressure is a constant, equals NCP dt. Cp is the molar specific heat at constant pressure, not constant volume. Okay, when the pressure is constant, using the first law of thermodynamics, we write dQ equals d internal plus pdV. dV is no longer zero, rather P is a constant. You see, you have this extra term, right? So basically the idea is, as you add heat to it while maintaining the pressure, as you add heat to it, of course, the temperature is going to rise, right? As the temperature rises, imagine this ideal gas. If the temperature, if you absorb heat, yet you keep the pressure, what's going to happen to the volume? It's going to expand, right? Because if it does not expand as the temperature rises, its pressure will increase. Okay, so dV is positive, which means the heat added to the system is not only used to increase the internal energy, it is also partially being used to do work, to expand. And therefore, that is greater than dQV for the same exact change in temperature, dt. Therefore, you can imagine that Cp is greater than Cv because it takes more heat to raise the temperature by the same amount. Again, that's partly because the energy, the heat absorbed, is not only responsible for changing the internal energy, it is also responsible for doing work by expanding. So the question is, what is pdV equal to? Well, it is rather easy to calculate it in our case because after all, P is a constant. Now remember, PV equals nRT for an ideal gas, right? So therefore, I can differentiate it, okay? So I have dPV. Now remember, P is a constant, I'm going to take out a differentiation, so that's pdV, right? Isn't that equal to nR dt? Right? So we learned that as long as the pressure is a constant, pdV equals nR dt, which I plug in, so I replace pdV with nR dt. All right. Now, that leaves d internal. But d internal equals ncv dt. We learned that before. That's what CV, that's how we got CV, right? So, d internal equals ncv dt. I combine these two terms, take out dt, take out n, I have n times this thing times dt. But isn't that the same as ncp dt by definition? By the definition of Cp. Therefore, it turns out that Cv plus R must equal to Cp. Okay, so Cp equals Cv plus R. That is from the very definition of Cp and Cv, and the first law of thermodynamics, of course. So, the molar specific heat of any ideal gas, there are, if you look at two kinds of molar specific heat, constant volume and constant pressure. It turns out Cp is always greater than Cv by a value of R. Now, why is it greater than Cv again? It's because, again, if you want to raise the temperature of a certain ideal gas by dt, under two circumstances, okay, one at constant volume, the other at constant pressure, it takes more heat to do so at constant pressure because if you do not allow the volume to change, then the thing cannot do any work. So all the heat that goes in is to increase the internal energy. But if you keep the pressure the same, then not only do you give it enough energy to change its enough heat to change its internal energy, you must also do something extra. You must also give it heat to allow this thing to expand to do work. That is why Cp is greater than Cv. It takes more heat to raise the temperature of an ideal gas at constant pressure versus constant volume. Now, we can define a constant, a dimensionless value gamma, which is Cp over Cv. Since Cp is always greater than Cv, we know gamma, which is Cp over Cv, has to be greater than 1. Okay, to summarize what we learned about the specific molar specific heats of ideal gas, let's look at the value of Cp, Cv, and gamma for three different types of ideal gases: monatomic, diatomic, and polyatomic. Okay, we're talking about room temperature. For monatomic, Cv equals 3/2 of R. Remember, Cp is always Cv plus R, so that's Cp is 5/2 of R. And what's gamma? Gamma is Cp over Cv. So what you do is you take 5 over 2 divided by 3 over 2. That's basically 5 over 3. The answer is 1.67. For diatomic, V itself is 5 over 2R. At room temperature, we do not consider vibration of degrees of freedom. Cp is always Cv plus R, so that's 7 over 2R. And therefore, the gamma value is 7 over 2 divided by 5 over 2. That's 7 over 5, and the answer is 1.40. And for polyatomic, you have 3R here, right? And Cp, you add another R, is 4R. So therefore, the gamma value is 4 over 3. And that gives us 1.33. These are the theoretical predictions as to what these values should be. Why are we interested in gamma? Because this has to do with an important special case called adiabatic process. What is an adiabatic process? Okay, there are two ways to realize an adiabatic process. You have a tank of gas, right? Suppose you suddenly change its volume very quickly, increase or decrease volume. Okay? Or you can change it slower, but you must make it a good insulator. You use a very good thermal insulator around it, so you do not allow heat to go in and out. Anyhow, adiabatic here means no thermal exchange, no heat exchange. Q is equal to 0. That is the very definition of an adiabatic process. This can be realized if a process is really fast. You change the volume of gas very quickly. There is not enough time for heat to go in and out, so Q is pretty much close to 0. Or, like I say, you have very good thermal insulation, which does not allow heat to go in and out. The adiabatic process is totally different from constant volume process, constant pressure process, or constant temperature process. Okay, it's something very unique. Now, how does one represent a adiabatic process on a PV diagram? You know, for a isothermal process, that's constant temperature process, you know P times V equals a constant, right? So P times V equals a constant. That's when T is a constant, isothermal. Basically, it's a line, it's some sort of curve, you know, it's actually a hyperbola that goes down like that. The adiabatic process, you can imagine, if you suddenly increase the volume of a tank of gas. If you suddenly increase it, but you do not allow heat to go in and out, there is no heat exchange. When the thing suddenly expands, it has to do work, right? When it has to do work, it must lose energy, and there is no heat it takes in. So there is nothing that compensates for the work it does. Therefore, its temperature is going to decrease. Okay, so its temperature decreases plus volume increases. Therefore, you know what happens. That is, its pressure will have to decrease. So whether it's isothermal or adiabatic, as volume increases, the pressure will have to drop. Okay, now here is something interesting. I want to draw these two lines, an adiabatic line and isothermal line. I want to see if these start from the same point, from same initial state. Okay, I have an adiabatic line and an isothermal line. I want to see which one is above the other. Okay, which one is above the other? Okay, I can of course derive the equation of state for adiabatic process. In fact, we're going to do that in just a minute. But the thing is, I don't have to do that. Even before I do that, I can show, based on the first law of thermodynamics, that the adiabatic line must stay below the isothermal line. So if I draw a blue curve and a red and a green curve, the blue curve is above the green curve. Therefore, the blue curve must be the isothermal. The green one must be adiabatic. Now, how do I know that? Okay, I'm going to use the example to show you how to use the first law of thermodynamics to figure things out. Here is the idea. Let me imagine that an ideal gas starts from this initial state, and it makes what's called a cyclic process. What's a cyclic process? It means it makes one whole round. It goes back to itself. That's what it means. Okay, it goes back to itself. It makes a whole cycle. Now, when something makes a whole cyclic process, here is P, here is V. I want to know this. I want to know what is the total work done by this thing. The total work done by this thing. Okay, see, from here to there, the thing is expanding, right? When expanding, it does positive work to the environment. How much work did it do? That will be this whole area, right? Next, from here to there, it shrinks, right? As it shrinks, it does negative work. Okay, so how much negative work does it do? That much. So you take the positive work, which is this area, minus the negative work, which is that area, you get a total work done. So what's the total work done? It is equal to the area enclosed. You see that? That area represents the total work done by an ideal gas in a cyclic process. Okay, and if the process goes on clockwise, then more work is done by the gas, less work is done by the environment, so the work done overall is positive. If it goes backwards, then the total work done by the gas is negative. That's one thing. Another thing is, what is the total change in energy, in internal energy of this ideal gas when it goes back to itself? Well, that's simple, because the ideal gas, or anything for that matter, the energy is a function of state. Okay, you give its pressure, you give its temperature, you give its volume, whatever, all the necessary parameters. Then the temperature is uniquely fixed. The energy of the system is uniquely fixed. And since the thing came back exactly where it came from, it regained all the original parameters. It's back to the original state, and therefore the energy should go back to the original value. So delta E is equal to 0 for the entire process, as long as it is cyclic. Okay, with these two things in mind, let us look at how we can construct a cyclic process from this diagram to show that the adiabatic line must stay below the isothermal line. Here's how we do that. We can assume that the adiabatic line is above the isothermal line. And I want to show that this will lead to something not acceptable. That is a violation of the first law of thermodynamics. Okay, let's see now. Suppose this line above is adiabatic, okay, and the green line below is isothermal. So you start from initial state, you go adiabatic, so that's Q equal to 0. Okay, Q equal to 0. Let's call this process 1, going from here to there. And then, once you reach this point, you go down without changing in volume. Okay, so this line is perpendicular to the v-axis, so the volume does not change, and that's called step 2. Once you are at step 2, you take a ride along this isothermal line, you go back to the initial state. So obviously, this is a cyclic process, step 1, 2, and 3. The total change in energy is 0. The total work done is positive, okay, because the total work done equals this area. And that is positive. Now, how does that violate the first law of thermodynamics? Let's see now. What is the total, Q is equal to 0 from here to there, right? Let's look at the heat absorbed from here to there. From here to there, the volume does not change, yet the pressure drops. When the pressure drops, what happens to the temperature? Well, the temperature decreases, right? Because the ideal gas law, the temperature decreases. Remember, the internal energy of an ideal gas is proportional to its temperature. So when the temperature drops, so does its internal energy. So going from here to there, it doesn't do any work to the environment because V is equal to 0, yet its energy drops. How come? Well, that only means that the system has lost some heat to the environment, right? That's why its energy drops. So Q2 is less than 0. Here's Q1. Q1 equals 0 because it's adiabatic by definition. Now, look at the third step. Okay, from the third step is isothermal. What does isothermal tell you? Isothermal tells the temperature does not change. And again, since the internal energy for an ideal gas is proportional to its temperature, when the temperature does not change, that means the internal energy does not change. Meanwhile, the system goes from a larger volume to a smaller volume, so it shrinks. As it shrinks, the environment does positive work on it. I squeeze it, right? So the environment does positive work. Normally, that would mean the temperature would rise, right? You compress the gas, the temperature would rise. How come the temperature does not rise? That means whatever work done by the gas, by the environment, must be leaked out as heat. Okay? So let's say somebody did 100 joules of work to the gas to compress it, but 100 joules of heat is leaked out. Therefore, there's no change in its internal energy. That tells us for the third step, going from here to there, the heat must be leaving the system, so Q3 is also less than 0. So Q1 is equal to 0, Q2 is less than 0, Q3 is also less than 0. So for the entire cyclic process, Q is less than 0. Because that would be Q1 plus Q2 plus Q3. That is less than 0. Okay. Q is less than 0. The work done by the gas is positive, you see, right? The work done by the gas is positive. What about the work done on the gas? The work done on the gas, by definition, is negative. W equals a negative value. This is the work done on the gas. What does the first law of thermodynamics tell us? The first law of thermodynamics tells us that Q equals delta E internal minus W. Right? That's what the first law of thermodynamics is. Okay, this is the heat absorbed. This is the change in internal energy. This is the work done on the gas. Now take a look. Q is less than 0. Okay, so this term is less than 0. W is less than 0. That's the work done on the gas. So negative W is greater than 0. All right, now what does that tell us? You have a negative value here, you have a positive value here. So do you think delta E internal can be 0? No, because on the left hand side you have negative value, right hand side you have a positive value, so delta E has got to be less than 0, right? But wait a second, this is a cyclic process. It came back to itself. So what do you think delta E should be? 0. Okay, so this is equal to 0. So you have a contradiction. On the left hand side you have a negative value. On the right hand side you have 0 plus a positive value, so it's positive. So therefore these two are not equal to each other. And are we bothered by that? Of course, because that is the first law of thermodynamics. How can this be invalid? Okay, therefore this cyclic process, this imaginary cyclic process, can never be actually realized because it violates the first law of thermodynamics. And what is wrong with it? It is because we have misplaced the isothermal curve and the adiabatic curve. We assumed that the adiabatic curve is above the isothermal curve, and it turns out that leads to a violation of the first law of thermodynamics. So it is wrong. So what is the real adiabatic curve? We know it has to be below the isothermal curve now. Okay, it has to drop steeper, but exactly what is it equal to? So this calls for what's called adiabatic equation of state. We're going to now derive explicitly the equation of state within the adiabatic process. Adiabatic process means dq equal to 0. There's no heat exchange. dq equals d internal plus pdv. That's the first law of thermodynamics. ncv dt, that's for dE internal plus pdv. Okay, we have all three values here, t, p, and v. I don't like that. What I want to know is, for example, can I eliminate t in favor of p and v so that I will have a relation between p and v in an adiabatic process? Well, we can do that. Okay, the idea is we're going to use the ideal gas law, PV equals nRT. This is true for any process, adiabatic or not. As long as it's in thermal equilibrium, you have a temperature T, you can always use PV equals nRT. Now, let us work it out. PV equals nRT. I want dt, right? I want dt. So therefore, let me differentiate both sides. Okay, let me differentiate both sides. I have PdV plus VdP. Right? I'm differentiating d of PV. What is that equal to? That's nR dt. Okay. So what really is dt? dt is PdV plus VdP divided by nR. I'm going to plug that dt in. So what does that tell me? It tells me NCV times dt, which is PdV plus VdP over nR plus PdV equals 0. Okay, equals 0. Now n and n cancels. I'm going to move that r to that other side. So there is an r here. I don't have that r anymore. And I know what r is. R is, isn't it true that Cp equals Cv plus r? So isn't it true r equals Cp minus Cv? Okay, I'm going to replace r with Cp minus Cv now. Plug it in. Okay, so I have here Cp, Cv, P, dV. I'm just copying this. Plus Cv, V, dP. Plus Rp dV. Okay, R is replaced by Cp minus Cv. So Cp minus Cv pdV. And that equals 0. Take a good look. This term Cv pdV. There's another term Cv pdV. You see, they cancel each other out. Right? This term cancels this term. So I only have two surviving terms: Cv VdP and Cp pdV. So let me work it out. Cv VdP plus Cp PdV equals 0. Now I'm going to divide everything by Cv, so that Cv is gone. I have Cv right here. This is actually Cp over Cv, as you know. What is it equal to? Isn't that just gamma? Okay, so I have VdP plus gamma P dV equals 0. At this point, I can integrate over P and V, but before I can do that, I must separate the variables P and V. So what I'm going to do is we move P to one side and move V to the other side. That is very easily doable. Let me first move this term to the other side. VdP equals negative gamma P dV. Right? Gamma is P over C. Move it to the other side. There's a negative sign here. And then I'm going to get rid of that V. I'm going to put all the V to this side, put all the P to that side. So basically I'm dividing everything by PV. Okay, so this term is now dP over P. The other side, negative gamma. You divide this by PV, so that's dV over V. We're now ready to integrate. Integrate. This is the natural log. Here is the natural log as well. So you have natural log of P equals negative gamma times natural log of V. Move that negative gamma inside. That equals to log of V to the power gamma. Negative gamma, that is. Okay, and then I can write this. Actually, let me move this term to that side. It's actually easier to do it that way. That's log P plus gamma log V equals 0, right? And then I'm going to move that gamma in, so V to the power gamma. Okay, so log of P plus log of V to the power gamma equals a constant. Now log A plus log B equals log of AB, so that's log of P V to the power gamma equals a constant. Since the natural log of this thing is equal to constant, this thing itself is also equal to a constant. So there we go. We have the adiabatic equation of state. P V to the power gamma equals a constant. You can see indeed this agrees with our analysis based on the first law. That is, this curve has to be steeper than the isothermal curve. Isothermal curve is P V to the first power equals a constant. Here, gamma is always greater than 1, right? If gamma is always greater than 1, this is going to be steeper because V is amplified by this power factor gamma. So as V changes, it's going to change more rapidly. P is going to change more rapidly. Okay, so this is the adiabatic equation of state. As an application of the adiabatic process, let's revisit the problem of the speed of sound. You know, in chapter 17, we derived the speed of sound formula. V sound equals the square root of B over rho. B is the bulk modulus, rho is the density of the medium, and B, the bulk modulus, is defined as negative 1 over V dP dV. If we assume that the propagation of sound is an isothermal process in which the temperature does not change, then if we assume this is an ideal gas, PV equals nRT, we can calculate that B, okay? Because T is a constant, so PdV, d of PV equals 0, which means PdV equals negative VdP. From that, we can calculate B. Negative 1 over V dP dV. In fact, you take dP and move that dV over there, and negative 1 over V, and you find this is just equal to P, the ambient air pressure. And you plug that in, okay, and you find that the speed of sound is P over rho. Now, at standard temperature and pressure, P equals 1 atm, which is 1.01 times 10 to the 5 Pascal, right? You divide this by the density of air, that's 1.29 kilograms per meter cubed. And if you finish this calculation, you'll find the speed of sound to be around 280 meters per second. And the problem with that is that this does not agree with the speed of sound value at STP standard temperature and pressure, which is around 330 meters per second. Okay, this is the real value. There is a significant difference between these two. And Sir Isaac Newton came up with some explanation. So he assumed that the air has water vapor in it. You shouldn't consider water vapor. The air molecules has its own size, and you shouldn't consider the air sound traveling through the molecule itself. That sort of thing. But what is the real reason why we have such a big discrepancy between the theoretical calculation and the actual value? Well, the real difference is that as the air gets compressed, decompressed, compressed, decompressed, as the sound wave travels, the compression process is very rapid. Okay, a typical sound wave has frequencies of several hundred to several thousand hertz. So the air actually gets squeezed, de-squeezed, squeezed, de-squeezed thousands of times a second. This process happens so fast that we can think of it as an adiabatic process instead of the isothermal process, because as the air gets squeezed, there is not enough time for heat to go in and out, and therefore the temperature will rise. It is no longer an isothermal process, but rather, as a better approximation, is an adiabatic process. So if it's an adiabatic process, then what is the value of B? Well, let's recalculate it, shall we? We have P v to the power gamma equals a constant this time. Okay, and then we take a differentiation. Right? We have v to the power gamma dp plus gamma v to the power gamma minus 1 p dv. Now that equals a constant, right? And if we divide everything by v to the power gamma minus 1, then we have v dp equals negative gamma p dv. From that, we can calculate the value of B. Okay, B is negative 1 over V dP dV. And the difference here, there's an actual gamma. You compare these two expressions. Okay, there's an actual gamma here, and that will tell us, if you did all the calculation, you'll find that this B now becomes, instead of P, it becomes gamma times P. There's an additional value, gamma, sticking out. This means I have to replace this by gamma P instead of just P. Okay, there is a gamma here coming out, and gamma, if you use air as a medium, that's a diatomic gas. Gamma is 1.40. Okay, so our formula originally was missing a factor, which is equal to the square root of 1.4. What is the square root of 1.4? It is equal to 1.18. So our formula was 18% too low. You multiply this by 280. What do we get? We got 331. Okay, so with that, you recover the correct value around 330. So this becomes remarkably accurate if we add this gamma in. So this is an application of the